Okay, we're going to do a very exciting thing now. We have seen on the very first day of this unit that if you add up all of the numbers from 1 up to some point n, then this is n plus 1 over 2. Okay, that's a very exciting formula, and okay, since presenting you with this, I also asked you to read section 9.1 of the textbook, which introduces you to the details of sigma notation, which is something you maybe kind of learned last year also, potentially, with Mr. Kirk, not sure. So using the language of sigma notation, we can write this out more clearly as the sum from I equals 1 to n of I. In other words, start counting, it's just kind of like a basic loop type structure. Start counting at I equals 1, so that's 1, and then kind of increments by 1 every time, so you're adding 1 plus 2 plus 3 and stop when you get to n. So this is kind of a succinct way of writing what's going on here with the dot dot dots. Alright, so that's like a formula. That's kind of exciting. For various reasons I want more formulas. I want to know what the sum of the squares are. So what is 1 plus 4 plus 9 plus 16, the perfect squares, all the way up to something n squared. So what is this? In sigma notation, what I'm looking for is a formula, kind of like my previous formula, but now, you know, a different one, for the sum from I equals 1 to n of I squared. And the thing is, I don't know what this is. Okay, so, right. How are we going to come up with this? There are a bunch of ways to come up with this. One is, someone can just tell you the formula, and then you can check it via some advanced technique that we're going to learn about soon. Another thing you could do is try to discover it kind of geometrically. Recall that to be interpreted 1 plus 2 plus 3 plus 4 as sort of the sums of dots. So, you know, 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4. And then we said, I wonder what is 1 plus 2 plus 3 plus 4? And we said in this other video, well, if we think about this geometrically, if we think of this as kind of like a triangle, then you could sort of stick another copy of it in there, and you have this kind of triangle, and you have this sort of original triangle. And okay, if I want the sum of the numbers from 1 to 4, then, or maybe just 1 to n, that's n, and that's n plus 1. And that's kind of like a visual proof that if you multiply n by n plus 1, then you get 2 of these things, and that's kind of a proof of this formula. Okay, so perhaps if I want the sum of the squares, perhaps what I should be doing is pursuing some kind of visual proof. What happens when you take like 1 plus 2 plus 3 plus 4 or something like that? Okay, and actually, you know, we can do this. And this is probably maybe the deepest and most kind of satisfying way to do this problem. But we're not going to do that right now. What I want to do today is a kind of a more of an algorithmic, sort of numerical, algebraic way of coming up with this formula. So the goal for today is to sort of discover what this formula is. What is the formula for the sum of the squares of the numbers? Okay, and right. So let me erase this, because I think I need some space. But maybe I'll just kind of leave up in the corner or something, you know, with the goal. The goal is to find out a formula for the sum from I equals 1 to n of I squared. Okay. To come up with a formula for this in terms of n, as a function of n. All right, now I've been teaching this for years. I know exactly, you know, what to do, but maybe it's a little confusing why you would want to do this. All right, so here comes an intro, which I have sort of attached to the beginning of this lecture, to make it all kind of seem more intuitive or something like that. So here we go. Take first a, okay, so what we need to do, if we want to add up the sums of the squares, well, okay, first an observation. Take a linear function, like 3x plus 5. This is something you learned last year. What can I say about this linear function? Well, let's just kind of plug in some numbers and see what happens. So, 1, 2, 3, 4, 5, something like that. Okay, well, plug in 1, you get 8. 2, you get, what are we doing? We're just adding 3 every time. So, yeah, 9, 5, 14, 17, 20, etc. Okay, great. Actually, what I just kind of said out loud is exactly the key to this, right? Which is that this linear function should be interpreted as, well, if you check up on it at discrete intervals, fixed intervals, then what you really see is that this is an arithmetic sequence, and that we're going up by 3 every time. So this is kind of characteristic of linear functions, which is that they increase at a constant rate. This is like fundamental principle of algebra 1. You spend like a month or something in algebra 1 repeating again and again this big idea that linear functions have a slope. What's the slope? It's sort of the rate of change. In this case, the rate of change is 3 because for every increase of 1 along the horizontal axis, the function increases by 3. Okay, great. So linear functions increase at a constant rate. All right, good. Going faster. Take y equals x squared. Wow, this is exciting. Again, I think you did this last year, almost this exact conversation. So this is kind of review. So 1, 2, 3, 4, 5. Okay, and this is 1, 1, 4, 9, 16, 25, etc. Okay, great. Some more light on here. All right, how fast does a quadratic increase by? Well, if you have never seen this before or you forgot, it's actually quite an exciting sort of moment. Okay, from 1 to 2, this quadratic goes up by 3, then the quadratic goes up by 5, then by 7, then by 9. Whoa. In other words, quadratic functions increase at a rate which is itself increasing. These numbers are going up. So quadratics, as you kind of know already, are going up each time by more and more. So there's sort of no such thing as the slope of a parabola, or there's no such thing as a parabola having a constant slope, because the rate at which this parabola is increasing is itself increasing. And by how much is it increasing? Well, it's increasing at a linear rate. And that can be seen by taking the finite differences between 3, 5, 7, and 9. In other words, as is sort of obvious, these blue numbers are linear with a slope of 2. Okay, so if linear functions increase at a constant rate, then quadratic functions increase at a rate which is linear, and which is to say the second finite differences are constant. Okay, and now let's kind of do the last one. So we sort of recognize that these blue numbers are linear in a sense, because they have the characteristic property that linear functions have, which is that their finite differences are constant. Okay, so final one, take y equals x cubed, and now I think I need to go out to like 6 or something. 2, 3, 4, 5, 6. Okay, and let's see, what are my perfect cubes? 1, 8, 27, 64, 125, 216. Okay, let's investigate, keeping our color scheme or something, the finite differences. Okay, by how much does a cubic increase? Well, here I go up by 7. Here I go up by, 19. Here I go up by 37. So that's plus 37. Here I go up by 61. And here I go up by, I don't even know what that is, 91 or something? What is that? No, oh man, 75 and 16, yeah, 91. Okay. Well, here's the thing. I kind of recognized 3, 5, 7, 9 as being like, the odd numbers or whatever. I do not recognize 7, 19, 37, 61, 91. Those are some numbers, but what kind of function this is, I'm not really sure. And I want to know. Well, one thing I might do to it is reveal its nature by checking its own finite differences. Okay, so by how much, at what rate is this blue function increasing, you might say? Okay, well, we've gone up by 12, we've gone up by 18, we've gone up by something. What is that, 34? Did I even do that right? No, 24. 24, yeah. And we've gone up by 30. These numbers I recognize. 12, 18, 24, 30. That's an arithmetic sequence. In other words, this I recognize as being a linear function. And how do I know it's a linear function? Because I know that the finite differences of that are constant. So plus 6, plus 6, plus 6. Okay, so because these numbers are going up by 6 each time, then this must be linear. And I also know that it's like quadratic functions which increase at a linear rate. And so, this, I'm going to put here, this is going to be some quadratic. Okay, what's the big idea here? This is basically calculus, by the way. Linear functions increase at a constant rate. Quadratic functions increase at a rate which is linear. Cubic functions increase at a rate which is quadratic. And you're supposed to believe that this is quadratic because the rate at which it is changing is linear, and this is linear because the differences are constant. Alright, what is the whole idea, therefore, about all of this? Well, the big idea here is that somehow I should be looking here if I want to find the sum of the squares. Why? Because this right here is some quadratic function. I already wrote that, I'm just writing it again now. This is some quadratic function. And so one thing I might do, if I want to find the sum of the squares, is to add up all the terms of this quadratic function. But here's the thing, if I add up 7 and 19 and 37 and 61 and 91, well, what do I get? Well, if I do 1 plus 7, I get 8. Plus 19, I get 27. Plus 37, I get 64. Plus 61, I get 125. Plus 91, I get 216. In other words, if I'm willing to think of these as, so here's the fact, right? The fact is that 1 plus 7 gives me 8, plus 19 gives me 27, plus 37 gives me 64, plus 61 gives me 125, plus 91 would give me 216. 216 really can be thought of as 1 plus the sums of all the differences in the cubes. To write this a little bit differently, what is 7? 7 is 8 cubed minus 1 cubed. What is 19? 19 is, 2 cubed minus 1 cubed, so 8 minus 1. What is 19? 19 is 3 cubed minus 2 cubed. What is 37? 37 is 4 cubed minus 3 cubed. What is 61? 61 is 5 cubed, make sure I'm doing this right, minus 4 cubed. And what is 91? 91 is 6 cubed minus 5 cubed. And if I add all those up, what do I get? I am going to get, of course, 6 cubed minus 1. Okay, and when you write it like this, it's just obvious, right? Because look, 6 cubed minus 5 cubed, but then plus 5 cubed, but then minus 4 cubed, but then plus 4 cubed. And that's actually easier if you write it sort of like the other way or something. Okay, okay, so what or something? It's because these numbers are quadratic. And since these numbers are quadratic, then I kind of know how to add up a bunch of quadratic numbers. The answer is that when you add up a bunch of numbers which are quadratic, one can think of those quadratic numbers as differences of cubes, and therefore I can find it this way. In other words, suppose I want to add, how do I do this? Yeah, suppose I want to add 91 and 61 and 37 and 19 and 7 and 1 together. Okay, well, how do I do this? Well, I just think of 91 as 6 cubed minus 5 cubed. I think of 61 as 5 cubed minus 4 cubed. I think of 37 as 4 cubed minus 3 cubed. I think of 19 as 3 cubed minus 2 cubed. I think of 7 as 2 cubed minus 1 cubed. And I think of 1 as 1 cubed minus 0 cubed. And now, this is, you should feel, although this is a little bit obscure what's going on here, but you should feel that this is the kind of thing I'm looking for. This question mark down here in the bottom left-hand corner is sort of what I want, right? What I want to do is find some formula which will let me add up a bunch of squares. In other words, I need to add up a bunch of quadratic things. Well, I should be thinking to add up a bunch of quadratic things lets me phrase those quadratic things as differences of cubes. And this is easy. What is 6 cubed minus 5 cubed plus 5 cubed minus 4 cubed plus 4 cubed minus 3 cubed plus 3 cubed minus 2 cubed plus 2 cubed minus 1 cubed plus 1 cubed minus 0? It's just 6 cubed. This is what we say. We say that this sum telescopes. That's the official math term for this, and that's because it kind of collapses, right? It's like I have a thing, and then I subtract something, but then I add it back. I subtract something, but I add it back. I subtract something, but I add it. All these numbers go, and this is kind of like one of these like old-fashioned telescopes, like pirates use or whatever. And then you kind of, when you're done with it, and then you just kind of like go and you like swoop and you put it together. So this is called a telescoping sum, and there it is. Okay, this is an extremely long buildup, which terminates right now with the realization that to discover the formula for the sum of the squares, I should look at differences of cubes. Okay, and so that's just what I'm going to do right now. Hopefully what I'm about to do flows smoothly from what just happened. So let me erase. And yeah, and now get ready to go. And here is the get ready to go. I need a formula. And what I need is a formula for the difference of cubes. I want the difference between a cube and the previous cube. So, alright. Based on your amount of background knowledge, you either know how to do this, or you don't or something. So, yeah, I want a formula for this. So, I want a formula for the difference between a cube and the previous cube. It's exactly the thing I was calculating a minute ago. 6 cubed minus 5 cubed, 5 cubed minus 4 cubed. I need a formula for it in general. Okay, there's a bunch of ways to do this. If you just know the formula for the cube of a binomial, then that's kind of nice. If you don't, then you always have the option of just kind of cranking it out, I guess. So maybe I'll just show it for the people who don't know, which is most people. Then we just kind of tediously do this, right? And what happens? Okay, I get a cubed minus 2a squared plus a minus another a squared plus 2a minus 1. And I guess some things, what have I done? Have I done that correctly? Sure I have. So this becomes a cubed minus 3a squared plus 3a minus 1. And when I subtract, I get 3a squared minus 3a plus 1. Okay, I kind of want to erase this for space reasons. So let me just write it over here as a math fact. Math fact: if you take a number cubed minus the previous number cubed, then you just do get 3a squared minus 3a plus 1. Okay, so without any more build-up, let's now discover the formula for the sum of the squares. And here's what we're going to do. We are going to look at differences of cubes. So let's take, let's see how I want to do this. Let's take n cubed minus n minus 1 cubed. Well, what is that? Well, I just derived this formula here, which tells me that n cubed minus n minus 1 cubed is 3n squared minus 3n plus 1. Okay, great. Now, do it again, but go one less. So now, n minus 1 cubed minus n minus 2 cubed. This is exactly what we had written on the board 5 minutes ago with 6 cubed minus 5 cubed, 5 cubed minus 4 cubed, etc., etc. You should sort of feel this as being kind of familiar. Well, now I want to write this out in a kind of a pattern. So looking up here, what do I have? What is the difference between a cube and the sort of the previous cube? Well, it's like 3 here. Well, okay, I guess the simplest thing to say is that here a is n minus 1. So this is 3 n minus 1 squared minus, trying to keep this nice and neat, 3n plus 1. So this is 3n minus 1 plus 1. Just try it like that. Okay, looking good. Okay, yeah, I mean it's just this formula, but a is n minus 1. Hopefully that's clear. All right, let's do it again. N minus 2 cubed minus n minus 3 cubed. And, well, now, again, it's just the difference between a cube and the previous cube. Just let's use this formula. A is now n minus 2. So then this is 3 n minus 2 squared minus 3 n minus 2 plus 1. Okay, and, well, we're going to do this, a lot. Keep writing these equations. Of course, n is in general. So we're going to, keep going until you get to, I don't know, how about 3 cubed minus 2 cubed? What is that going to be? So I'll throw in some dots because I skipped a whole bunch of lines. But, well, now it's just this same formula, but now a is 3. So this is 3 times 3 squared minus 3 times 3 plus 1, And, okay, what's 2 cubed minus 1 cubed? Well, it's just the same formula, but now a is 2. So that's 3 2 squared minus 3 2 plus 1. And, of course, by the way, that's just 7 on the left. So this better be 7. 12 minus 6 plus 1, so that's looking at good. Final equation, 1 cubed minus 0 cubed, is 3 times 1 squared minus 3 times 1 plus 1. Okay, what have we done? We have just written out n equations. Each of those equations is of the form a cubed minus a minus 1 cubed. But we set them up in such a way, well, maybe I'll just say it right now. What we're going to do with these equations is we're going to add them. And the entire left-hand side, just as before, kind of by design, telescopes. Because I have n cubed minus n minus 1 cubed plus n minus 1 cubed minus n minus 2 cubed plus n minus 2 cubed. Minus 2 cubed plus 2 cubed minus 1 cubed plus 1 cubed and then minus 0. So the entire left-hand side when I sum up these equations, the sum of the left-hand sides of all the equations is just n cubed. Okay, next question. What happens when I sum up all of the right-hand sides? Okay, well here we've written it out sort of neatly, so hopefully it's clear what's going on. What am I doing here? I'm adding 3 times 1 squared plus 3 times 2 squared plus 3 times 3 squared plus all the way up to 3 times n squared. So in fact, this entire gigantic column is just 3 times the very thing I've been looking for this entire video. This is just going to be 3 times the sum from I equals 1 to n of I squared. So the goal of this whole thing kind of emerges in this calculation. Okay, wait, let's keep going. I have something more to say in a second. What's next? Well, I'm adding minus 3 times 1, minus 3 times 2, minus 3 times 3, all the way up to minus 3 times n. What's that? That's just negative 3 times 1 plus 2 plus 3 plus 4 all the way up to n. So this is just the sum from I equals 1 to n of I. But that's something I already know. Okay? And finally here I have 1 plus 1 plus 1 plus 1 plus 1, but I have n of those, so this is n. Okay, this equation I have written right here is quite amazing, though you still might not sort of see where this is going. It's exactly as I promised, right? I said a couple of boards ago, but of course I erased it, that when you sum up the differences of all the cubes, what you get is, at the moment I called it sum quadratic. And the sum quadratic that you get is this one. This sort of 3 times the sum of the squares minus 3 times the sum of the numbers plus a sum of a bunch of ones. And now, since I already know what this is, I can kind of work backwards to find out what this is. In other words, well, maybe I'll just kind of keep going right here in the same spot, right? I have n cubed equals 3 times the sum from I equals 1 to n of I squared minus 3 times what happens when you add 1 plus 2 plus 3 plus 4 all the way up to n. That's the formula that we already know. It's n plus 1 over 2. And then plus n. So, by doing some algebra now, what do I find? I find that the formula for the sum of the squares is just a couple of lines of algebra 1 away. What is it? It's n cubed plus 3n n plus 1 over 2 minus n all over 3. I just took this one and I just moved that over to the other side and moved that over to the other side and divided by 3. Okay, so I've run out of space, so I think I will controversially, kind of erase half my board, even though I'm in the sort of middle of the derivation. Or I suppose I could just kind of squeeze it in. Maybe it is better to kind of squeeze it in up there or something. I don't know. Okay, let's see. What do I have? I have a third, kind of way on the outside or something, and then what is that numerator? I think I should get a common denominator and sort of multiply things out. So that's 2n cubed plus 3n squared plus 3n minus 2n over 2. Hopefully that's clear what I did. That's 3n squared plus 3n. Yeah, and then I just got a common denominator here, 2 over 2 and 2 over 2. And okay, this is looking good. So what do I get? 1/3. Well, I might as well just call it what it is, right? It's some stuff over 6. What is that stuff? 2n cubed plus 3n squared plus n over 6. And of course, I could just stop there, but I could also factor out an n. And if I factor out an n, I get 2n squared plus 3n plus 1 over 6. And that quadratic also factors. It factors into 2n plus 1, n plus 1. Okay. Wow. The final answer is that if you add up 1 plus 4 plus 9 plus 16 plus 25 all the way up to n squared, the answer is n plus 1, 2n plus 1 over 6. This is an amazing formula that we've derived, and the key idea here is that this way of doing this is recursive, because the entire process depended on me already knowing the formula for the sum of the integers, positive integers. And now that I know the formula for the sum of the squares, there's nothing that's stopping me now. If, suppose, teaser, suppose I want now to come up with the formula for the sum of the cubes. And by the way, I do want to do this, and you're going to do this problem for homework. How should I do this? Well, you just repeat the entire process. To find the sum of the cubes, I need to add up a bunch of cubic things. But to add up a bunch of cubic things, I should think of those cubic things as the differences between quartics. And so I want to now do a to the fourth minus a minus 1 to the fourth, and figure out what that is. Then I'm going to write n equations, and when I add them all up, as I've done here, it's going to give me an expression which will have the thing I'm looking for and also the other things. Okay, this is kind of hard to explain. So if you get it, you get it. Good. And you're going to do this for homework. Goodbye.